we will have one presentation, but unfortunately Danielle was not well today, so we had the second talk will not take place today, but different day. So we'll have more time as you need. But yeah, maybe we'll finish earlier. So Serene, graduate student from Nathan Weaven, we just heard from her recently about her experiences as a doing internship. So now it's on the PhD project. So please, thank you.
I'm very sorry if you all showed up here to hear Daniel talk about nonlinear spectroscopy. Instead, it's just me talking about path integrals. I'll be talking about actually I think this title is perhaps a little bit misleading because it says algorithms plural, but I'm only going to be talking about one out of the 3 algorithms in this paper because I thought I would only have 20 minutes and I didn't want to go super into detail about like 3 algorithms because they would not fit in 20 minutes. So there's only one single algorithm that I'll be talking about in this talk. And here's the archive link for the paper. So I guess first, very brief motivation. Why simulate quantum physics on quantum computers? Maybe this isn't necessary because I'm sure people already know this, but the Hilbert space of quantum systems scales exponentially with the system size. So if you want to simulate this on a classical computer, just storing the wave function will take exponential space, and then actually doing the operations also computationally difficult. And I didn't want to put like the super cliche Feynman quote about how like nature is quantum, so we should use quantum computers to simulate them. But I'm sure you all know the quote. So the gist of that quote, basically. So why use the path integral formulation? So the path integral formulation is a different alternative formulation of quantum mechanics, but it is equivalent to the Schrödinger representation. And usually in quantum simulation, like Hamiltonian simulation, we call it Hamiltonian simulation because it uses a Hamiltonian. It's usually the Schrödinger representation or sometimes the Heisenberg representation, but usually uses a Hamiltonian. But the path integral formulation is very widely used in physics, especially quantum field theory. It has some benefits, like sometimes the Hamiltonian isn't easy to find or write down. And the Lagrangian is also Lorentz invariant, unlike the Hamiltonian. However, with classical simulation of path integrals, where you do Monte Carlo sampling of the paths, you end up with a sign problem because you have such variance in your samples because of all the different phases in the paths. At worst, you end up needing to take an exponential number of samples in order to reconstruct your time evolution. So maybe quantum computers could offer a solution to that. So could we do path integrals on a quantum computer? So the path integral formulation of quantum mechanics is derived in continuous space within infinite space, and qubits are discrete and finite. So can we take the infinite continuous path integral expression and then just discretize it and put it onto a quantum computer? One issue with this is that the unitarity of the path integral formulation isn't readily apparent. So that's one benefit of the Schrödinger representation. You have a Hamiltonian. The Hamiltonian is Hermitian. You exponentiate it. You end up with a unitary operator, and unitary operators are the natural operations that you perform on a quantum computer. So that's very nice. But in the path integral formulation, even though the time evolution should still be unitary, just by looking at this expression, it doesn't really look like it is a unitary operator. So if you're just discretizing the continuous path integral expression, it's not immediately clear that you end up with something that is unitary. And there are also a lot of paths to sum over. It's exponential in the number of time steps that you take. So what we did instead was that we started off from scratch from the discrete from the Schrodinger equation on this discrete qubit space, and then we derived like a discrete version of the Feynman path integral from that. And this algorithm can be generalized to higher dimensions, like higher spatial dimensions and particle numbers. But for the sake of this presentation, in order to keep it from getting too messy, I'm just going to stick with one particle in one space dimension. Yeah, so just a quick background about the path integral formulation of quantum mechanics. So it was worked out by Feynman in his PhD thesis based on ideas previously developed by Dirac. And the motivation behind coming up with this new formulation of quantum mechanics was to formulate a quantum analog of to the stationary action principle, or the principle of least action in classical mechanics. And in classical mechanics, if you have a particle, the trajectories that solve the Lagrange equations of motions are the stationary points of the action functional, which is the time integral of the Lagrangian. And the quantum analog of this that Feynman derived is that the evolution of a quantum system is a sum or an integral over all trajectories going from one initial position to a final position. So it's sort of like a sum over all the possible paths that you could take from one point to another. And you can see that in the classical limit, if you take h bar going to 0, what you end up getting is a phase that oscillates a lot. And by the stationary phase approximation, the most dominant paths, because of all the phase cancellation from all the other paths, the most dominant paths in this expression will end up being the stationary points of the phase, which sort of gives a very natural classical limit to quantum mechanics. Yeah, so now I'm going to set up the derivation for the algorithm. If any of you have seen the path integral derivation, like for example in your Q of T class, this will basically follow the steps very closely. So yeah, we're going to start off with our Hamiltonian p squared over 2m plus v of x, and then since we're working in a discrete with a discrete finite number of qubits, we're going to have some position domain that we're working in from 0 to x max, and the assumption is that all the dynamics is constrained within that position domain. So we're going to divide this domain into 2 to the n positions, where n is the number of qubits, and then we're going to use the computational basis states to represent each position. So if we have some computational basis state q, then q represents the x position q delta x. And then we can also define position and momentum operators in the space. So x is going to be diagonal in the computational basis. So v of x, since it's a function of x, is also going to be diagonal in the computational basis. And then the momentum operator is going to be, as in the continuous case, the Fourier transform of the position. And here Q of T is the quantum Fourier transform. So in the qubit space, that's just the equivalent of the Fourier transform. Yeah, so now that we have this Hamiltonian, now let's look at the transition amplitude from one initial state Qi at t equals 0 to some final Qf at capital T. So the Schrodinger equation tells us that the time evolved state is e to the negative iht times the initial state. So if we look at the overlap between Qf and Qi, it's sort of looking at some time evolution, the overlap after some time evolution e to the negative iht. And what we can do is divide this time evolution into R different time steps. So now we're doing e to the negative IHT over R times. And then the next step is to, as in the continuous path integral formulation, if you've seen this derivation, we insert resolutions of identity between each time step. So in the continuous case, resolution of identity would be integral over ket x, bra x, dx, and then integrating over all of space. In this case, since we have discrete and finite number of states, we have a sum going from 0 to 2 to the n minus 1. So we do that between each time step. So the way that you can sort of interpret this is that these q's in between, you're going from qi to q1 to q2 and so on, and summing over all possible paths going from qi to qf. This is sort of cut off at the bottom. Yeah, so now if we zoom in and look at just one particular time step in the full time evolution, what we can do is apply the Trotter product formula. So the Hamiltonian is the sum of a kinetic and potential term. So we can apply the Trotter product formula to split this into two separate exponentials, and we're going to end up accumulating some error that scales with the norm, I guess in the worst case, with the norm of the commutator between the two terms. And it also scales with t squared over r squared. So the idea is that we want to take r to be large enough that this error term is going to be negligible. So for now, I'm just going to ignore the error part, but I guess we'll come back to it later. So yeah, just going to drop the error term for now. And what we can do is apply the V operator to the computational basis state QK. So since V is diagonal in the computational basis, QK is some eigenstate of V. So we can just directly apply the operator to the state and just get the eigenvalue in the phase. And what's nice about that is that now we no longer have the operator V. It's just V if QK is a scalar. So we can sort of just take it out. And now we want to do the exact same thing with P. We want to get rid of the operator. So in order to do that, we're going to insert another resolution of identity, but this time with the P eigenstate. So again, this is very similar to the derivation of the Feynman path integral, which you may have seen before. And here, the eigenstates of the P operator are the quantum Fourier transform of the computational basis states. So we're inserting that over there. And then you can see that you can apply the P operator to the P eigenstate to get the P eigenvalue in the phase. And then take these inner products between P and Q, and then do all the math to obtain something that looks like this. So you have a sum where you have a phase that's quadratic in P. And if you've seen the continuous path integral derivation, you would know that here is where you go to Wikipedia and look up like list of common integrals in QFT, and then you solve this Gaussian integral, and that integrates out your P states, and you no longer have any dependence on P. But in this case, we have a discrete sum, so it's a little bit more complicated than that. But it turns out there is a theorem, the reciprocity theorem for generalized quadratic Gauss sums. And it has an expression that looks a lot like this one. You have something that's quadratic in n, which I guess in our case is P. But the thing with this theorem is that it holds, you have specific requirements for what the coefficients are. So A, B, and C have to be integers. You need AC plus B to be even. And if we look at this expression over here, we have this coefficient in front of the p squared. So in order to apply this formula, we need this part to be an integer. So that actually puts a restriction on what R has to be. So R has to be, if we're setting this to be 1, then we have R needs to be exactly equal to this function of Tm x max and delta x. So we can do so R also needs to be an integer because it's the number of time steps. So we can do that by adjusting x max and delta max so that we have an integer value of R. So you can always just make your space bigger or smaller, and changing your grid size in order to make sure that that's satisfied. But yes.
This the requirement on R just ensure that you can calculate the sum.
Yeah. And it also ensures that the expression that you end up getting out of the sum looks like a Lagrangian.
And is the end goal sort of to cancel the intermediate like 2k plus 1 and everything?
It's to cancel like the p sum, like so that there's no summation over p.
This is one time step, right?
Yeah, this is for one time step.
Yeah, the closed form expression for qk plus 1.
So we're summing over all the qk's and qk's plus. So yeah, this is for one time step for one like fixed value of qk and qk plus 1. But in the whole expression, we need to sum over all of them. Yeah, so it turns out with this requirement, if you plug in this expression into the formula on the previous slide, you end up getting something that looks very much like a Lagrangian. So this is after plugging in, the definition of Q being equal to, or xk being equal to Q times delta x, doing all the algebra there. This is what you end up getting, and this is pretty much just the Lagrangian. So pretty cool that you can end up getting something that looks very similar to the continuous Lagrangian, which is that. So instead of x dot or the time derivative of x, you have xk plus 1 minus xk divided by the time step. Yeah, so this is the transition amplitude for one time step. And if we look at the entire time evolution, you just repeat this R times and sum over all the QKs. And this product over all these exponentials, you can just sum up the phase. And this expression over here, so it's like the Lagrangian at each time step summed over all the time steps. This is pretty much the discretized version of the path integral, where you have the time integral of the Lagrangian. So instead of a time integral, it's a sum over like small discrete time slices. So if you took R to go to 0, or took R to go to infinity, then you would end up getting something that looks like an integral in the phase. And yeah, the expression looks pretty similar to the continuous one. And the cool thing about this is that this operator that you get out of this expression is going to be unitary because it was exactly derived from the unitary that we got out of applying the Trotter product formula. So even though this expression, just from looking at it, it doesn't necessarily look like it's unitary, it actually is exactly unitary. And because of that, it can be implemented on a quantum computer. So yeah, as a summary of what the operator is sort of doing, like sort of an intuitive explanation of what's happening, is that every path in this path integral, or in this case, I guess path sum, you have a sequence of Qs, and each path picks up a phase that's equal to the Lagrangian times the time step size, and that happens at every single time step. So you pick up a phase along each path, and then the entire time evolution is just the sum over all such sequences of paths, like all possible paths going from Qi to Qf. Okay, so now I'm going to be talking about the algorithm to actually implement this. So for one time step, this is the unitary operator that we're applying, ignoring constants, because we can just sort of pull out the constants and phases and like constant phases all out to the front. So this is sort of like, for example, if you have like 2 qubits, so 4 computational basis states, like each basis state gets mapped to a sum of all the other basis states where each evolution picks up the corresponding phase. So this is sort of like a visual representation of like one time step. So we're going to assume that we have some oracle that gives us access to the Lagrangian in the phase. So this access model is pretty different from the Hamiltonian access model because it doesn't use a Hamiltonian operator. The Lagrangian phase is a scalar. It's just a scalar in the phase. And also, it does give the Lagrangian and not the full action, but I just thought action oracle was a much cooler name. Sounds like a, I don't know, really cheesy superhero. So yeah. And it turns out that we can get all these transitions that we need with the proper phase by combining this action oracle with a quantum Fourier transform. So if you recall, we needed to map each state to a superposition over all the other states, which is exactly what a quantum Fourier transform does. So each time step can be implemented with 2 oracle queries and 1 quantum Fourier transform. I'm not going to go through the math here of like showing exactly how it works. I guess you'll have to read the paper for that. And just as a reminder, this is what the quantum Fourier transform looks like. Maps one state to superposition over all the other states. And the number of gates required is it scales with n squared, where n is the number of qubits. So returning back to how we chose R, now talking about like the error analysis and all that. So R needed to be this very exact expression. And recall that we use the Trotter product formula, and the number of time steps that we take when we're doing the Trotter product formula determines the Trotter error. But we need R to be exactly equal to that. So in order to change R, we have to change delta max and X max. So this gives a pretty unusual restriction on the scaling on the discretization in time and in space, because now the position discretization is directly tied to your time discretization. So if you want a more finely sliced grid, you also need to take more steps in your time evolution, which is kind of interesting. But the position discretization, the number of position grid points that you take only scales logarithmically with the number of qubits, because you can store 2 to the n positions in n qubits. So it's actually not too bad. Yeah, so another thing is that the Trotter error scales in the worst case with the commutator between the 2 operators, p squared and v. And in the continuous case, we know the commutator between p and x. It's constant. So that's not too bad. But interestingly, p and x in the way that we've just defined this discretely doesn't have a constant commutator, even in the limit where we take delta x goes to 0, which is a little bit weird, but like mathematically, that's sort of the way that worked out with the way that we defined it. So yeah, it turns out that this naive commutator bound will grow faster than increasing R will shrink the error. So in order to combat this, I guess we just can't use the naive commutator bound. So yeah, we need to restrict ourselves to physically realistic systems. So we can't let, like we can't let the momentum go extremely high. We can't have like super large potentials. So everything has to be bounded by some constant, which is like physically risky, yes. Delta x is the size of the grid spacing. Yeah, so each Trotter time step, it's t squared over r squared, and since it's multiplied by r, then yeah, it's t squared over r. Yeah, so we need to assume that the system and all the observables that we would be measuring on the final state stay within some subspace with bounded momentum and potential. And if that is the case, then we have an overall complexity that scales with O tilde of t squared, p max squared, v max over epsilon. So the tilde hides like the polylog factors because if you're increasing the number of time steps, you're also increasing the number of qubits, or yeah, you're increasing the number of qubits logarithmically because the number of x grid points scales logarithmically with the number of grid points.
Is this hypothesis compatible with the inequality?
In what way?
To decrease the error on the position delta x, shouldn't the error on the limit increase? Variance, like your position like error is delta x, it goes to you decrease it, but shouldn't p also increase? That's
So I guess we have restrictions on the types of states that are, so I didn't put all the details of, I sort of just said everything stays within some allowed subspace, but it would be some subspace where the states are such that you don't get like momentum blowing up or anything.
Is it like the fixed energy subspace?
And I guess the actual time evolution doesn't have a momentum operator per se in it, because if you crawl back in the expression for like this expression, it doesn't actually have a momentum operator. So we're not really ever measuring the momentum of the system in any way, if that makes sense. I don't know if that answers your.
We saw that the modulus of p goes one of the x squared.
Yeah. So I guess that would be like in the worst case, if you're considering the Trotter error to scale in the worst case with the norm of the operators, which for a physically realistic system, like under physical constraints, usually is not the case that the error would scale with the norm of the operators.
Also, these p and x operators are not the same p and x, right? Otherwise,
it's like the p and x that was defined like at the beginning, like the discrete versions.
So
yeah,
the commutator is not constant.
Yeah,
they are different operators, so different formulas.
Yeah.
And when you say complexity, what do you mean, number of gates?
Yeah, so it's both number of Oracle queries and number of additional gates. So I guess it's assuming that the Oracle can be implemented with a constant number of gates. So yeah, that's sort of it for this one algorithm out of the 3 in the paper. So here, I've shown that the exactly unitary discrete version of the path integral can be defined on a qubit space, and that this path integral formulation can be efficiently simulated on a quantum computer. And yeah, again, there was this unexpected time-space discretization constraints where the size of your time steps scales with the position grid spacing. For future work, maybe looking at more interesting Lagrangians. So for this particular case, like we kind of needed that quadratic form of the Lagrangian in order to apply the Gauss sum formula. But maybe there are other ways to derive unitary operators out of different types of Lagrangians. And looking at applications to quantum field theories. And as I mentioned, there are other algorithms in this paper. There are 2 more algorithms on Hamiltonian path integrals where we don't go through the whole process of coming up with a Lagrangian. So if you don't have something like, p squared plus v of x, you can just stick with the Hamiltonian formulation, and where you insert the resolutions of identity, you still do that with like the Hamiltonian terms. Yeah, so it's I'm giving another like 1 hour talk on this next week. So like I'll probably, if you're gonna be going to that talk, I guess you'll hear about the Hamiltonian path integrals, or you can look at the paper, which is here. So yeah, that's it from me. Yes.
I know that does a future work prospect, but do you have any ideas on how to handle, in general, this discrete half-integral derivation for like more general Lagrangians?
I think looking at more Gauss sums, like I got a book from the physics library that I think I've had for like 3 years on like Gauss and Jacobi sums, and I think if you had something that looked a little bit different, there's probably some other way to like sum out certain terms in order to get something that looks like a Lagrangian. So I think that would be the next thing to look at.
Yeah.
Very nice presentation, thank you. I wanted to ask, what would be the benefit of using, let's say, this algorithm over Newtonian evolution? Like, is it you can parallelize things here? Like,
yeah, so you can parallelize things, but I guess the main thing is that it's a different access model. Like the oracle that we've defined here is different. Like you don't need to know the Hamiltonian terms or anything. And yeah, this is in a lot of ways sort of like a stepping stone towards more complicated path integral simulations. It's a pretty like basic Hamiltonian that we started with, but maybe in the future we could do stuff that's more interesting, like quantum field theories.
Have you indeed tested it in this manuscript on a concrete example?
No, I haven't looked at any. I haven't done any numerics either, but the math works. So
it's last word.
With these action oracles, do you just need to specify an oracle for the v of x? Like, you just need to be able to compute that?
yeah, and I guess you also need to you need to build the quadratic part of the kinetic. So yeah, you need to, it would act on like 2 states that have the like the 2 positions, and then yeah, you need to build the like kinetic part and the potential part, but just like as a scalar in the phase.
Oh, v of x is that.
Yeah.
Green. So if you have a system of Lagrangian dynamics, how hard is it to convert that to Hamiltonian dynamics?
For like quantum mechanics, like just basic quantum mechanics, like it's pretty straightforward. For quantum field theories, it's harder to find the Legendre transformation sometimes between the Lagrangian and Hamiltonian formulations. Like for this case, like we know what the Hamiltonian is because we started with the Hamiltonian. So but there are probably some other cases where it's not that straightforward to just do the transformation.
Okay, thank you very much.
Yeah.